Welcome to Excel Business Statistical Analysis video number 13. And in this video, we got to talk about measures of variation and dispersion. Now, most of the time in a stats class, when we get to variation, people's eyes glaze over. They don't get it. But I promise, with one visual, we'll understand what variation means and why it's so important. And then we'll get busy calculating range, variance, standard deviation, and even coefficient of variation, with the standard deviation being the most important calculation you'll learn about in this video. Now let's learn about variation and why it's important. Now we have three data sets and three visuals to help us understand dispersion or variation. Here's a column of hours worked per week for job number 1, and there's a mean of 35. Now I plotted that mean right there, and all these data points below the mean of 35. For job number 2, whoa, it's exactly the same mean. I plotted it here, and I took all the data points and plotted it right below. Just looking at this visual, can you figure out which data set has more dispersion or spread in the data or variation in its data points compared to the mean? I think you guessed right. It's the data points from job number 1. In addition, for this first data set, understanding dispersion visually here can help us answer the question, which mean more fairly represents its data points? Well, clearly this one does, because the deviations, that means the distance between each particular value and the mean, all these deviations are small, whereas these deviations are big. And if you use this mean in conversation like, hey, my average hours worked per week is 35. Well, when you use both of these 35 for these data sets, that mean right there is going to represent more accurately all these data points than this one. Our second example involves gas prices. Here's gas prices from Variance. Here's gas prices from Seattle. Now notice the mean at the bottom, they're not exactly equal, but we can use dispersion or variation to ask the question, where are gas prices more volatile? Where volatility just means which city has more up and down in the prices. So here's Variance 256 right there. Up and down would be the distance between each particular gas price and its mean. The mean of $2.66 per gallon in Seattle is plotted here. The volatility comes from the deviations. So which city seems to be more volatile in their gas prices in relation to the mean? Well, it's hard to tell from this visual. Certainly when we calculate our measure, in particular standard deviation, then we'll have a number that we can compare. But right off the bat, it looks like the volatility or the dispersion or variation or spread in the data is bigger in Seattle. The third example comes on V3. These are orders made, and from Banderson Company, these are the number of days it took once we placed the order to get the custom birch plywood to make boomerangs. From this second company, Plywood and Floor, these are the number of days it took from the order to getting the wood. Now look at this. Both of the means are 9. That means on average it took 9 days from Banderson, from ordering to getting the wood. And same with Plywood and Door. On average, 9 days. Now, if you think about 9 days to get an order, that's a very important number for business planning. But when we plot Banderson right here, there's a 9. Here's all the data points. Here's Plywood and Door. There's the 9-day mean or average, and there's all the data points. From a business perspective, which company would be more reliable? That means for you planning your business, when you place an order, can you use this mean and rely on it? Certainly this one right here, Plywood and Floor, since the deviations seem to be much smaller for Plywood and Door than Banderson, it seems like planning day-to-day activities would be easier and more reliable when we use Plywood and Floor. And later we'll have a measure, and it will measure exactly what is called the standard deviation, and that will tell us how reliable this mean is, and in this case, how reliable our supplier is. Now, those are three examples visually, and there's a number of different ways we can create a measure to calculate variation or dispersion. And for most of our examples, we're going to use this example here. Days to fill an order from Banderson and Plywood and Floor. Now on the sheet variation formulas, you can Control P and print this out. It has all my notes about variation. This is a duplicate. On our original note sheet at the beginning, all of this information is there also. Now let's go over to the sheet V4. All right, here are the number of days to fill an order, and we want to calculate X bar, or our mean, equals average. And you can use your mouse, but I'm going to do up arrow, and then hold Shift, and then up arrow. And notice those will be relative cell references. So when I Control Enter, I can copy this to the side. If I look, F2, the reference moved as a relative cell reference. All right, the first measure of variation or dispersion or spread in the data is range. And it makes sense. We want to see what the min and max is, and then figure out what the distance between those are, called range. So equals the min function, and we'll get our relative cell reference. And for the time being, I'm going to hit Enter and then calculate the max using the max function, and Enter. And then we'll calculate the difference, max minus min, and Enter. Now I want to copy all three of the different formulas to the side at the same time. So I highlight, hover over the fill handle, and when I see my angry rabbit, I click and drag. So for Banderson, we have a min of 4 days. That's pretty good. I wish all the orders came in 4 days. But a max of 16. And look at that. The total range is 12 days. For Plywood and Floor, a min of 6, a max of 11. But notice the distance between those is just 5. So from a planning point of view, it seems more reliable here. Now the problem with the min and the max is it only uses two values, the extreme values, the min and the max. Another way to calculate the spread or the range or the dispersion is to calculate the interquartile range. That's quartile 3 minus quartile 1. This will calculate the range for the middle 50% of the data, and it overcomes the sensitivity of the extreme data values. Now I have quartile 1 and 3 here, and we have our two data sets. So we'll use quartile, and I'll use .inc, the array as a relative cell reference because I'm going to copy that to the side, comma. And for quart, I just want 1 and 3. But guess what? I'm going to hit the F4 key to lock this, because when I copy it to the side, I want the blue one to move, but not the orange one. Now, when I Control Enter to put the formula in the cell and keep the cell selected, because this is a spilled array, watch this. I don't have to highlight both cells like I did up here where I highlighted all 3 cells, because each cell had a different formula. When I'm copying a spilled array, I just have to copy the top cell. When I do that, it spills first quartile and third quartile. When I hit the F2 key, bam, it got both of the ranges correct. Now quartile range equals quartile 3 minus quartile 1, Control Enter, and copy it to the side. So for the middle 50% of the values in the first data set, the interquartile range is 6 days. Whereas for the middle 50% of this data set, the interquartile range is just 1.5 days. Now, the measure that we use most often for measuring dispersion or variation is standard deviation. And I'm going to use the built-in function to calculate standard deviation for both of these. But then we're immediately going to go over to the sheet V5, and we're going to calculate this longhand, because this calculation has a lot of intermediate steps before you get to the final calculation. And what it does is it'll add up all of the deviations for both data sets and then calculate a type of average of all the deviations. So for this first data set, Banderson's, The function is STDEV, and there's a dot P for population data and S for sample data. We'll use the sample data. And it's just like the sum or the average, max or min. We can enter one or more sets of values into the number argument. Now when I Control Enter and copy it to the side, check the cell F2, the range moved. And now we have the standard deviation for both of our data sets, 3.61 and 1.2. The bigger this number is, the more variation there is in the data set. Now the way this calculation will be calculated, and we're going to do it longhand, because when you do it longhand, the meaning of the measure is easier to understand. But the way we do it is we'll add up all of the deviations for each of the data sets and calculate a type of average deviation. So we can interpret this as, from a mean of 9, on average, the deviation for any particular order we get will be 3.61 days. Whereas here, from a mean of 9 days, the average deviation for any particular order is only 1.2 days. So clearly, this measure of standard deviation of 1.2 days tells us that plywood and floor is a more reliable supplier in terms of receiving our orders in a reliable and timely fashion. Now let's go over to the sheet V5. Wow, that's a lot of intermediate calculations before getting to the final result for our measure, standard deviation. But the bottom line is, here's all the particular x values. And from every one of those values, we have to subtract the mean. So the first calculation we'll make is we'll calculate the mean. There it is. When I hit Enter, I get 9 days. Now we need to calculate the deviation for every single one of those values. Equals, I'll highlight all of the x values. And from every single one of those values, I want to subtract the single value, the mean of 9. Now, because this is an operator and on one side there's multiple items, when I hit Enter, of course, the results spill into the worksheet. And there it is. 6 minus 9 is minus 3. Down here, 12 minus 9, we get a 3. Now, our goal is to add up all the deviations, divide by the count to get a type of average deviation. So we come to the bottom. Alt equals. It got the top cell and the spilled range operator because the formula only lives in the top cell. But when I hit Enter, I get 0. Well, here's the thing. For every data set you ever have to deal with, if you take the data points and subtract the mean and then add the results, it always sums to 0. So what did statisticians do to deal with the fact that the sum of the deviations is 0? Well, they did a few different things. One is they said, well, guess what? If we square it, meaning we square every single one of those, that'll get rid of the minus sign. But at the end of the calculation, then we have to undo the square here with the square root. Now, this is the most common way of calculating a measure for variation. If we scroll down here, here's a different formula you might see in a different textbook, but yields the same results. Here's also another one. And notice here, to deal with the fact that the sum of the deviations is 0, they didn't square. They took the absolute value. That's one way to do it. And all these formulas will give you similar results when you're comparing data sets. But here's the sample standard deviation formula we're going to use. So our next task is to take all of those values, caret 2 to square them. And when I hit Enter, I get a column of positive numbers. Notice minus 3 squared is 9. 3 squared is also 9. Now we come down here because our formula says please sum all those. So Alt equals and Enter. The next thing we need to do is divide not by the full count, but the full count minus 1. And when we're dealing with sample data, we have to divide by n minus 1. Now, the reason that we have to do this has to do with degrees of freedom and the number of values in the final calculation of the statistics that are free to vary. But the easy way to understand why we have to do this is because sample data, that means not all the data, but just some of the data, when we take the data and divide by the count, it tends to underestimate. So as a simple example of how n minus 1 will make the number a little bigger to compensate for underestimating, 10 divided by 5 is 2. But if you subtract 1, then 10 divided by 4 makes the result a little bit bigger. So we have to count how many observations there are. And you could use count on numbers, counta on text data. But I like to use rows. Then I can do it either on numbers or text data. So we have 15. And then 15 minus 1, that gives us our denominator here. So when we take the sum of the deviation squared and divide by n minus 1, making this calculation here, we calculate something called variance. Now, variance can be used to measure the dispersion or spread in the data set or the variation. But the problem is that the units are squared. So the way we deal with that is we take the square root, and in Excel there's a square root function, square root of 13, and there it is. 3.61 days is the standard deviation. Now, when we're calculating variance, there's a built-in function, and it has a p and an s. And if we have to calculate variance, all we do is highlight the values, and it does all the heavy lifting. If we have to calculate the standard deviation of the sample, well, as we saw just a moment ago, we don't have to do all of these steps. We just put in the values and hit Enter. But the reason that we did this is it's very important to see that we were trying to calculate a type of average of all the deviations. And sure enough, that's what we got. Now, that's calculating standard deviation the long way for Banderson's data. You can try plywood and floor data over here for practice. But if you get how the formulas work, all of these formulas can be copied over because these are aggregate functions that are looking at a relative cell reference below. So I can copy, paste over here. If I come to the bottom cell and hit F2, sure enough, that worked. That's why we use Excel, of course, because it's fast and easy once you get the hang of it. And these are spilled arrays. And so the formulas only live in the top cell. So when I copy and paste them over here, just like that, I have my deviations and my deviation squared. I can even copy these formulas, Control-C, Control-V. I can copy these values also since they're using relative cell references. And sure enough, it got the correct variation and standard deviation. So we calculated a sample standard deviation of 1.2 days for plywood and floor data, and a sample standard deviation of 3.61 days for the Banderson data. Now, this was sample data. Let's go over to the sheet V6. Here's the formula we used for sample data. Here's the formula you use when you have population data. And we use big N, and we don't subtract 1. That's the difference. We also use the Greek letter lowercase sigma to represent population standard deviation. And of course, mu, which is the Greek letter used for population mean. In Excel, you can use standard deviation.s or standard deviation.p. Here's a population, control down arrow. So it's got about 100 records. And the yellow ones are the ones that were randomly selected to create this sample. You can see when we used the sample version, we got $3.53. Here on all the population data, we got $3.65. The sample standard deviation is rarely exactly equal to the population standard deviation sigma. But in this case, it's pretty close. In later chapters, we'll learn methods to determine if the sample mean is reasonable as a point estimator. Now, we want to go over to sheet V7. Now, sometimes you want to compare relative variability or dispersion in two different distributions. For example, here we have a mean bonus paid per year of $2,000 with a standard deviation of $755. But over here, we have a mean years worked of 15 and a standard deviation of 3 years. How in the world can we compare standard deviation in this case? Not only are the means really far apart, but the units are totally different. Well, the way we do it is with coefficient of variation. And the math formula is simple. We take standard deviation and divide it by the mean. That will convert standard deviation to standard deviation per 1 unit of mean. And you use this measure of variation when the data are in different units or the data are in the same units, but the means are far apart. So here we go. Ready? Equals, there's the numerator, standard deviation, divided by a mean bonus of $2,000. When I hit Enter, this tells me the amount of standard deviation per 1 unit of mean. And now we can use this to compare to our second coefficient of variation. Over here, equals, well, there's the standard deviation divided by the mean. And when I hit Enter, that tells me that there's 0.2 units of standard deviation for every 1 unit of mean. And now that we've converted to coefficient of variation, we can compare these two numbers and see that this distribution has much more variation than this distribution. Now, in this case, the units were completely different, so we had to use coefficient of variation to compare variation in the data sets. But down here, we have two wage data sets, one from city 1, one from city 2. So if we calculate the mean for this first city, the wage data, Enter, and then the standard deviation for the sample. All right, I get a mean of $22.64. So that's the average wage data in that city with a standard deviation of about 10 bucks. Now I'm going to copy these aggregate formulas with relative cell references and paste them over here. Whoa, in this city, the average wage is 37 bucks, and the standard deviation is almost $30. So since the means are so far apart, we can use coefficient of variation to compare the variation or distribution in the two data sets. We take standard deviation and we divide it by mean to get standard deviation per 1 unit of mean. So 0.47, I'm going to copy that and paste it over here. 0.75. So clearly there's more variation in city number 2 wage data set than there is in the city number 1 wage data set. Now I'm going to turn off the dancing ants with the escape key. All right, our last example, we want to go over to V8. Now here we have stock A returns and stock B returns. And as we learned a few videos ago, when we want to calculate the true compounding rate per period that we can use to calculate end and beginning amounts for stocks or other growth situations, we use the geometric mean to calculate that mean. But oftentimes, and especially in finance when it comes to stock returns, people do use the mean and the standard deviation. And for standard deviation, they use it to calculate the volatility or the risk of the stock. That means the risk of the stock going up or down. Now here's the mean for stock A, and there's the dispersion in the data set. Here's the mean for stock B. Here's the dispersion in the data set. What it means by volatility or risk, it means if you make an investment, well, sometimes you might have a huge loss or you might have a huge gain. But with this stock here, yes, you're never going to have some gigantic loss or gigantic gain, but all the returns seem to be clustered together. So that mean is a good gauge of the return you might get for any particular period. So in this case, we can use the standard deviation, and this is a sample, so we use the S. And remember, when you calculate standard deviation, it uses the mean. So we'll calculate standard deviation for stock A. So it looks like 11% or 0.11. And actually, I could have copied this over because this is a relative cell reference. And it looks like here we get a standard deviation of less than 1% or 0.00945. So clearly, stock A has more volatility or risk because for any particular period, the value can fluctuate above and below the mean by a large amount. But stock B, the volatility or risk is much lower. because for any particular value, it's not going to fluctuate much above or below the mean. All right, in this video, we talked about various measures for variation and dispersion. We looked at a stock example. On sheet 7, we talked about coefficient of variation when you're comparing data sets that are in different units or the means are far apart. We talked about the two different formulas for sample and population standard deviation. We calculated standard deviation longhand. We looked at our Banderson and plywood and floor example and calculated range, interquartile range, and standard deviation. And then we saw 3 visual examples of how variation or dispersion can be useful for understanding your data and making decisions. All right, next video, we're going to build on this video and take standard deviation and use it to calculate something called the z-score. All right, we'll see you next video.